All right, last time we started section 2.2, describing sets. We built in a little bit of vocabulary, talked about what a set was, collection of objects, elements, or the objects that it's the collection of. And we had some symbols that we saw last time. These are the ones, element, not an element, and some different number system kinds of things. And then we did two different ways of listing or including a notation for sets. So we're going to continue that discussion of sets with a little more vocabulary. Equal sets. Equal sets are two sets that contain exactly the same elements. Okay, so they are really the same. They're not just equal in the sense that they're identical, right? Identical sets are what equal sets are. A one-to-one correspondence is a pairing of elements between two sets, such that each element of one set is paired with exactly one element of another set. And then the third one on this slide, it switches over to the next one on your paper, but are equivalent sets. Equivalent, distinguishably different from equal. Equivalent sets are two sets for which there exists a one-to-one correspondence between the sets, i.e. the sets have the same number of elements. So, for example, when I was growing up, I had a brother, a sister, and my parents. There were 5 of us in our family. And my mom had a really good friend who was also the mother of 3 children. And she was married, so there was 5 of them in their family. So when we got together, everybody had a buddy, right? You know what that's like. And so there was this one-to-one correspondence because we had 5 people in our family, and she had 5 people in her family. So those sets weren't equal sets, but they're equivalent sets. They simply have the same number of people. Whereas at that point, if my mom would have described her family, as in the people living in her home and so forth, and my dad would have described his family in the same way, they would have been talking about the same grouping of people, exactly the same, right? The same, not just the same number of them, but the same people. And so those would have been equal sets. So we're going to take a look at how we decide how many one-to-one correspondences that there are between sets. So if you have 6 elements, is what this one's set up as, and you have your first person, okay? So you have 6 people in your grouping, and you have person number 1. So person number 1, we'll draw him as a dot. So here's, person number 1 from group A. So let's say group A has 1, 2, 3, 4, 5, 6, and we're numbering off their people. The second set also has 6 items, but I don't want to number them the same because I don't want to confuse the one in one and one in the other one. So we'll label them with letters. So they have A, B, C, D, E, and F. So this number 1 person has the ability to be paired with how many different people over here in group 2? 6 different people. So there's 6 different options that we can do this pairing for person number 1, right? But once we pair him off, and he's off in his pair with whoever he is, and we get to number 2, person number 2, how many choices does person number 2 have? Only has 5, because there's only 5 people left to pair up with, right? And what happens when we get to person number 3? They only have 4, and so it goes all the way down. So in some sense, you can sort of think of this as like having, I'm going to make 6 different numbers here. Person number 1 has 6 options, but once one of those options is taken off, person number 2 only has 5, and then there's only 4, and we continue to go down because pairings continue to happen with fewer choices that remain. And what we do is we actually multiply these to find out how many different total number of options we had. So if we take 6 times 5 times 4 times 3 times 2 times 1, grab a calculator. Tell me what you get. We did. Yeah, it comes up across lots of math classes, actually, this idea of pairing things this way. It's not always described this way, but yep. 720 correspondences. or pairings. Pairings is how this question actually words it, so only put pairings. That's the same thing, but there's 720 different pairings that could happen. So this has a notation. I'll mention it here, but it doesn't actually show up in your textbook here. But for those of you who are like, this looks like something I've done before, this is called 6 factorial. It's an exclamation point. Factorial just means you're multiplying all the numbers down to 1 after the number you're given. It works only for whole numbers. So if you had, like 7, you'd do 7, 6, 5, 4, 3, 2, 1, multiply them all together like that. So that works the same way here for these kind of one-to-one correspondences. It ends up being what are called factorials to do this. And so we're just multiplying the number of options and the ways that things can happen. It shows up in proportional and statistical reasoning, which is the other course the girls are talking about in chapter 9 is where it shows up. It shows up in contemporary math as well. I think that it was in chapter 3 in that book. Is either chapters 2 or 3 in the contemporary math book. So, and there's other courses through which it shows up as well. If you were doing this with young children, you do the same sort of thing, but you wouldn't do them with maybe as big of values, right? You do pairings where they actually write them out, not where they're just counting in their head how many they are and multiplying them. So, all right, cardinal number is the number of elements in a set. And it is written an N, and then some parentheses around the S set, the set S. And it literally means the number of items in S. So if we were to talk about the number of people living in my home right now, like full-time living in my home, that would be 6. Right? If we were talking about the number of people in this room right now, it would be 7. So it's just counting. It's just a counting strategy or a counting notation. A finite set is a set for which the cardinal number is a whole number. Right? 6, 7. If we counted the number of people at OBU, we can count that. It's a finite number. There is a number assigned to it. As opposed to an infinite number, which is a set for which the cardinal number is not a whole number. Right? Like how many counting numbers are there? There's infinite. Right? I can't put a number to that. So that's an infinite set. The last one is an interesting one. It's actually called the null set. This is a set that contains no elements, has a cardinality of 0, and it's written in a couple of different ways. It can be written as a 0 with a slash through it. Okay, so anytime I have students tell me that this is their 0, I have to say, I'm sorry, you can't use that for 0 because we're going to use it for something different, right? This means empty set. Or there's another one where you do a curly brace and you just don't put anything inside, which is a very sort of intuitive way of describing it. It's an empty set because it's a set and it's empty, right? And so there's lots of things that you can describe as empty sets. We're going to use it for some other purposes, but in particular, anything that would have nothing in it. For example, I could talk about the set I, and this set I is the infants in my home. It's 0. I don't have any infants in my home. So the cardinality or the number of things in this category is 0. Okay? So we're going to come back to this idea here in a little bit. But an empty set is simply a set that contains no elements. And you'll see how we're using it shortly, but that's what it means. All right, so on each of these, A through D, it's asking us to find the cardinal number. Now, we already learned how to do some of these counting strategies because we did Gauss's method. Do you remember that back in section 1.1? We talked about Gauss, and we started counting things there. So some of those are going to come back again, for another reiteration of that, trying to figure out how many of these things there are. So on A, set A is the numbers 9, 10, 11, all the way up to 99. How can I figure out how many of these there are?
99 minus 8?
Yes. So notice I started to do something wrong. Just a second. It won't be divided by 2. The division by 2 happened because we added numbers together. or if we skipped numbers, and this is not skipping. Okay, so what I was about to say is that, notice I started inadvertently to write equals. What I was writing was that the set was going to be equal to something, but that's not really what I'm doing. I'm finding the number of items. So the number of items in set A is equal to, and you're exactly right, Kaylee, the 99, and then you subtract the number that's in the sequence beforehand, which in this case would have been an 8. And what is 99 minus 8? 91. So this has a cardinality of 91. The second set, so n of b. So what can you tell me about this set? What do you notice that makes it uniquely different than the one before?
It's or adding to.
Yeah, it's adding to, or it's skip counting by twos, or it's only evens, right? Yeah, I don't have all the numbers. The last one had all the numbers between 9 and 99. This one only has every other one. All right, so we start the same way. We take the ending number and we need to subtract off what? 0, the number that came before. So we have 2002, and I need to subtract off 0. Here I do need to divide by 2. Why?
Because you're adding to.
Right, it's because I'm adding 2, or I'm skip counting by 2s, or I have only half of the numbers, so I'm only have half here, any of those kinds of descriptions. And if you take 2002 and divide by 2, what do you get? 1001. All right, C and D both look a little different. For starters, they're in more of like a set notation, right? Instead of that set builder notation than a listing method notation. C actually talks about having x squared values, and it tells you that x goes from 1 to 99. So all it's telling you is that you're going to take each of these, and the elements themselves in the set are the squares. So it's 1 squared, that's terrible, 3 squared, 5 squared, all the way up to 99 squared. Does the fact that they're squared have anything to do with how many of them there are?
No.
Not in the slightest. Okay? So it's not so much that it's meant to confuse you, but you do need to learn how to look at the important information as opposed to the set itself. You know, what am I trying to find? I'm not trying to figure out really what this set is, although this would be another way to describe it. I'm really trying to find out, see there I did it again, the number of items in the set. So I really just have the same thing that I had before I went and squared anything, right? This is my set. How do I find the number of items in my set? Yeah, so I'll start at 99. What would I have to subtract? Because this is a little one, the funny ones. Yeah, we subtract the number before it in sequence, which is -1. So minus -1. And then what? It'll end up being adding, you're right. What will I divide by? Because I do need to divide here. Yeah, divided by 2. Again, why am I dividing by 2? Because I'm skip counting by 2s. I'm skipping every other number, right? So you're right, Kinsey, it is 100 on top now then divided by 2, so I end up getting 50, right? 50 is the cardinality of set C. Our last one, n of d. Okay, so this says that I have the equation x equals x plus 1. It tells me that x is a natural number. That's what that notation means. So it's asking how many natural numbers are there that are equal to themselves plus 1. Huh?
Yeah.
Pick a natural number for me. 3. Okay. Does 3 satisfy this equation? No. It would be none. How come, Mackenzie?
Because no matter what equal to, they're adding one, it's not going to equal it.
Right. No matter where you start, if you add 1 to it, it gets bigger, right? And if it gets bigger, that's not going to be the same value you started with, and that's what this equation is set up to say. This is 0.
I feel like it's easy to understand, but like that, when you get all the symbols and stuff, it just
Uh-huh.
looks like really hard.
And so what I want you to realize is that when you get those symbols, write out a few of the things it's trying to sort of describe to see if you can figure out better what it's describing. Because when you saw 3 equals 3 plus 1, you were all like, well, duh, that's not going to work, right? But it was harder to see when it was written in symbols with the X's.
Well,
Yeah.
my thing is, what's all that stuff with the green line?
That says X is a natural number. You missed last class period, Kaylee, but we talked about it over here in this chart. This notation is natural number. Natural numbers are the ones we count with. 1, 2, 3, 4, and so on. Okay? And that symbol in between is telling you it's an element of. It just means it's one of them. So over here, when we encountered it again, it's just telling you that X is the numbers 1, 2, 3, 4, 5, and on up forever. That's the only numbers you can try here. So when we try these numbers in here, I don't need to try negatives, I don't need to try decimals, I don't need to try fractions or 0. I only need to be trying and working with natural numbers. Okay?
So do we not have to draw the line through our 0?
No, and that's a good question. This is actually counting. So all of these answers need to be an answer that's a number. I have 91, I have 1001, I have 50, and I have 0. If I were to rewrite this set in a different way, the set D is actually equal to the empty set. Right? That's what the set is. It is the empty set. But how many items are in the empty set? 0. So the answer to this question of how many is 0. Right? It would be like the difference between you asking me who is in your family and how many people is in my family. Right? This is who or what, right? The number people, pieces over there are the how many. So anytime you see that notation that says in of something, it's asking how many. Number of, not the set itself. All right. So Venn diagrams. Venn diagrams are used as early as 2nd grade is where I've seen them used. They might be used before that. Not necessarily for all the ways we're going to do that. I understand that. But Venn diagrams are diagrams used to illustrate ideas in logic. So what I specifically remember from my 18-year-old when she was in 2nd grade was they drew a Venn diagram. They had a partner, so she and somebody else partnered up, and they drew a Venn diagram. And the Venn diagram that they drew, a general Venn diagram, was 2 overlapping circles. So it looked, like this. And in the overlapping piece in the middle, we'll talk more about all these pieces, what they did is they put the things they had in common. Maybe it was their favorite color. Maybe it was the color of shirt that they were wearing. Maybe it was what they ate for lunch. Whatever. They put they put some things in the middle that they had in common. And then they put things on each of the other sides that they didn't share in common. So maybe my daughter had a brother and this little girl had 3 sisters. Maybe my daughter lived with both of her parents and maybe this little girl lived with her grandma. Whatever the scenarios were, there were things that they had in common and they put in the middle, and there are things that they don't have in common and they put them on the outside edges of the graph. Okay, so this is a Venn diagram. It talks about what things people share in common or what groupings or categories are in common and what things are different. The universal set of a Venn diagram goes around it. It's like this. It's a big old rectangle around it. And it's a set that contains all elements being considered in the discussion. So, for example, maybe she and her friend were supposed to be discussing food. Well, then any food would be in the rectangle. But the brothers and the sisters and the moms and the dads and the colors of their shirts, none of that would be relevant and wouldn't go in the picture. Right? So the rectangle sort of limits our discussion of what we're talking about. Right? And then the complement is the things that are given in, it says given a set F. This is the elements in the universal set that are not in set F. So it is written like this for this particular resource, this book. It draws a line on the top like that. The number theory, not number theory, that's one we're in. The contemporary math book that we uses a notation where it does a prime like this after it. And there are also resources that put a little C after it for complement. All of these are used interchangeably. The one we're going to be using is this first one because that's what our book does. So we're going to put the bar on the top of it. Okay, so imagine you had this rectangle and you just had one child that's describing, whatever inside of it. And so the category is foods, and the universal set is foods. And the circle in there is foods I like, and the outside of the circle is foods I don't. Right? So I might put, like apples in here, and I might put, cherries out here or something like that. So you're categorizing things that are in your category, and then they're still in the overall category, but they're on the outside of your circle. That's the difference. And if you were describing this, this would be called set F, and this area out here would be called set F complement, like that. And the whole box itself would be called U for universal, right? So universal includes the circle, and it includes the stuff on the outside of the circle, whereas F complement is just the outside of the circle. In terms of a picture, I'll color it in blue. All this blue part is F complement. Okay, so F complement is the stuff I've shaded in blue.
And then universal is the whole entire apples and cherries.
Yep, apples and cherries and everything else. You bet. Okay, so we're going to do a lot more in section 2.3 with Venn diagrams, but let's keep moving a little bit more with the finishing up of this section anyway. So let's call set U, or let set U be the set of all students at OBU. Okay? And A is the set of those who are graduating. Are you with me? We're going to describe the complement of A. What would A complement be described as?
Those not graduating.
Yes, from
OBU.
OBU. So this is the OBU students that are not graduating. Right? It still has to be OBU students. We still have to be within the universal set. So this isn't like all students that are not graduating. This isn't like, Shawnee High School students that are not graduating. We have to specifically say that we're still talking about OBU students, and they're the ones that are not graduating. Okay? Now, not only can we talk about sets, we can also talk about sets that are inside of sets, right? So like, let's say, for instance, I have this picture over here, and I did all kinds of fruit. I don't know why I was doing fruit with this, but I was doing fruit. And so we have a category that's food, right? That's the big square or the rectangle, whatever. And then we have a circle that's like healthy food, right? The stuff that's good for you. And then there's a circle that's inside of that that's sort of like, still has to be the healthy food, but it's like a specific type. It's vegetables, right? It's these embedded ideas. So you might sort of maybe imagining, the embedded Santa Claus dolls at Christmas time where they're inside of each other. It's kind of like that. So a subset. So for all sets A and B, B is a subset of A if and only if every element of B is an element of A. And it would be written like this. So it kind of looks like a C, like a squished C, or a U on its side with a line underneath it. So if you can imagine my example where I talked about vegetables, in order for vegetables to be a subset of things that are healthy, it has to be that every single vegetable that you put in that description is also a food that is healthy. That's what it means for it to be a subset. Everything in the set vegetables is also in the set healthy foods. You can think of the line underneath it, the line, like this piece underneath it, as sort of meaning or equal to. It could be the whole thing. You could argue that the only healthy foods, I'm not saying you should, but just for the purpose of the example I already gave, you could argue that the only healthy foods that exist are the vegetables. Well, if that's true, then that would mean that those are just two descriptions of the same thing. Healthy foods and vegetables are actually really describing the same thing, therefore they are really actually equal. So that line underneath it means you have the possibility of it being equal when you're describing it. Doesn't have to be, but it could be. Now, a proper subset for all sets A and B, B is a proper subset of A. If it's a subset, I mean, obviously, because that's part of the noun, right? Subset's the noun, proper is an adjective describing it. But it has to have at least one element of A that's not in B. So the moment you throw tomatoes in there, you thought tomatoes was a vegetable, tomatoes is a fruit. But you already said, man, tomatoes are healthy. Guarantee you tomatoes are healthy. Well, now there's one thing that's healthy, at least one, and it wasn't in the vegetable circle, right? So it's sort of like these embedded circles, but there's actually something in the outer circle. So picture-wise, let me picture-wise first, and then I'll do the other piece. You've got these embedded circles going on. Huh?
It looks like an olive.
It does look like an olive. I thought it kind of looked like an eyeball a little bit. This description right here about proper subsets is telling you there's really something out here. It's not just empty space. There's something in that space that makes these two sets not the same. Okay, it's not just a relabeling of the same description. It really is something different. It looks exactly like the same notation that we had before, but it doesn't have the equal to part on the bottom because it isn't equal. There truly is something smaller. B is truly smaller than A. It includes fewer items. We can count numbers of subsets as well. The number of subsets is based on the number of elements. So if you have n elements, then there are 2 to the power n subsets. And there's exactly one fewer, or 2 to the n minus 1, proper subsets. Okay? An example will help. Are you ready for one? Okay. All right, so this is actually, yeah, I fixed it. It used to be different in my notes, but it's been fixed in here. Okay. Consider the set of all mathematics faculty members at OBU. So in the math department, we have 4 faculty members. Dr. Tucker is our department chair. Dr. Marsh, some of you have probably had her. Dr. Drake, I know some of you have had him. And then myself. So there's 4 of us. So there's 4 of us. It says how many different subsets of the math faculty are there? So a subset is sort of like you say, that there's all 4 of us and we're in the room and we're like, okay, we're going to create a committee to do something. Well, how many people are going to be on the committee? Well, depending on how many people are on the committee will be depending on how many committees there are, right? We could just create one committee that's just the whole, all of us together. That'd be one of them. We could create a committee that has nobody in it, and therefore they're going to get nothing done. That's the null set, the empty set, not a very productive committee. We could call something a committee that has only one person, right? They're the representative that does something, whatever, and they have a job to do, right? A committee of 1. We could have committees that have 2 people at a time, and we could talk about how many pairings there are, right? How many ways do we pair up all the people? Or we could do committees that have 3 people. Okay, are you with me on creating these committees, how we could sort of structure that? How many committees are there? Well, the way that we can find the number of committees is exactly what this is describing down here. It's 2 to the power of n, and n is the number of items in your set. How many items are in the set of math faculty members? 4. So it would be 2 to the 4th. So what is 2 to the power of 4? Not 2 times 4, but 2 to the power of 4. 16. So there are 16 different possible committees that I could make. Or in the notation or the description, we're talking about subsets. There are 16 different subsets. Right? One of them's everybody, one of them's nobody. 4 of them are the individual people, one at a time. And then everything else are the groups of 2s and the groups of 3s that we could arrange. There's 16 different subsets.
I might have just not heard it. Where did the 2 come from?
It's part of the formula. It was given over here.
Okay. Okay.
Yes, for the purposes of what we're doing anyway. That's where we got it from. Yeah.
Got it.
Yeah.
Okay.
All right, so how many different proper subsets are there? Well, proper subsets from original subsets really easy. What's the difference in these 2 formulas down here at the bottom of the screen?
One
One subtracts 1. It's just one less, right? One fewer. So over here, if I know there's 16 subsets, how many proper subsets are there? 15, right? It's the same number as we had before, and then we subtract 1, so we have 15 proper subsets. Because we're eliminating the subset that includes everybody. It's not really a true grouping that's any different than I already have, so it gets eliminated. It's not a proper subset. You can use this formula in reverse as well. If you know the number of subsets or proper subsets, you can use the formula to figure out how many elements you have. Suppose you have a set and you know that there are 63 proper subsets. Well, the proper subset notation says this, right? Either from the standpoint of algebra, you can add the 1, or from the standpoint of thinking through how are proper subsets related to subsets, it's 1 less, right over here, this -1 business here, so I need 1 more. There are 64, 2 to the n is 64. So 63 was the proper subsets. (64) is the subsets. And then how do we figure out what n is? Well, there's lots of options. We could factor 64. That's an option. You're also welcome to use your calculator and try some options, right? Trial and error. 2 to some power. Well, 2 to the 6, 2 to the 7, 2 to the 10, 2 to the 12, 2 to something until I get 64. I feel like we paused, so maybe Kinsey found it. Did you find it, Kinsey?
No.
Not yet?
2 to the 6.
2 to the 6th. So 2 to the 6th is what Kaylee says hers worked out to being. So this here would tell us that there are 6 elements. Okay, are you guys with me? Barely. Barely. Okay. We have time for at least example 7, I think. And then we'll come back to example 8 and continue on next time. So we're getting caught up, just getting caught up very slowly. So we're making progress. There are 4 different statements here, and we're asked to use one of 2 different symbols. The symbol is either the element symbol or the is not an element symbol. Okay? So there's 2 things that you have to decide when you're working with this symbol. First of all, you have to decide, is it an element at all? Is it even describing an element? And then the second thing you have to decide is is it an element of the thing that actually is over on the other side? So that's sort of step 2. So on step number 1, we're looking for, is it even an element? So the first line, part A, what is that object that's on the left? We gave it a name before.
Null set?
We gave it the name the null set, or the empty set, right? It's something that, it is a set that contains no elements, right? That's what we described it as. Is it an element? Divided classroom.
Well, you said it's a set. A set is an element, right?
Nope.
Even though there's no elements in the set,
null
there's
is
still a
different
set.
than the 0.
Okay, so remember, think of it this way. You are each individually elements. The set is the collection of all of you. Is the set an element? No, it's the collection of elements, right? Math 1203 is not an element, it's a set. The hands family is not an element, it's the set, it's a group, it's a collection of elements.
But an element is in a set.
Okay, you guys are really overthinking this. This is called the null set. The word set is not the word element. That's it. That's all it takes. The word set is a set. It's a collection of things. It's a collection of things. It's not a thing itself. It's a collection of things. Right? Your contact list in your phone is a collection of people's names. It is not a name of a person itself, right? You can't say, call my contact list. But you can say, call my mom. Yeah? Okay? So the null set itself is not an element. And if it is not an element, we don't even have to talk about what happens next, because it's not an element to start with. There is one more among B, C, and D that is also definitely not an element. And it's C, because it's in the curly braces. The curly braces means I have a set. This is notation for a set. And if it's a set, it is not an element. So the first way to rule out things that are not elements is to rule them out as elements at all. Doesn't matter what came next. They're not elements to start with, so we can't even have the discussion. Now, B and D are elements, right? It's 15 and it's 16. Now, they may not be elements of what comes next, but they're elements. There's no curly braces around them. There's no set notation with them. This one right here, though, we have to decide, does it fit into this description? And if you don't know what the description describes, write a few terms out. Okay, we talked about this piece right here describing the numbers 1, 2, 3, and so on, right? That's what it describes. And you're putting them into this equation. So this is 2 times 1, and 2 times 2, and 2 times 3, and 2 times 4. What are 2 times 1, and 2 times 2, and 2 times 3, and 2 times 4? They're natural numbers, but they're more specific than that. They're skipping. Yeah, they are. There's a very special name for these.
Even.
Thank you so much.
Yeah.
They're even.
I think our brains are tired a little bit.
Well, we're almost done. Okay, are you guys good?
Yes.
2, 3, 2, 4, 6, 8, 10. Is 15 one of those?
No.
No. So it doesn't work, right? So this one fails to be an element because it's not in that description. It's 15, it's an element, but it's not an element of that stuff. It's not one of those. Take a look at D, though.
Is D not automatically out because 2, 4, 6, 8, 10, that's a set of numbers, right?
This is a set of numbers, 2, 4, 6, 8, 10. The set's on the right. Our question is 16 an element of that?
Yes.
Yes. Because what does the ... mean?
It keeps going.
It keeps going with that pattern, right? So the set that's actually being described here and here, these are the same set, just different notations. Set builder notation on set B, listing method on set D, but they're all even numbers. 15 is not an even number, but 16 is. So 16 is an element of the even numbers.
So only the first numbers have to be an element?
Correct. That's what we're deciding. Is the first number an element of what comes next? Yep. So we will pause there.